Hello and welcome to Module 2. I'm Sofia Tsokani. I'm Statistics Editor in Cochrane Method Support Unit, and in this session we will discuss statistical models and concepts in network meta-analysis. First of all, let's do a recap of what we have learned so far. Healthcare decisions should be based on all available and relevant evidence. By evidence, we mean studies like randomized controlled trials. Where we are interested in the comparison of two interventions, say A and B, for a certain health condition, we may find more than one study comparing them. Meta-analysis allows us to combine all the available information from different studies and obtain an overall effect estimate. However, for most of health conditions, we often have more than two interventions to choose from. That's where network meta-analysis comes in. Network meta-analysis extends the concept of pairwise meta-analysis and lets us compare multiple interventions in a single framework. It uses both direct and indirect evidence. With direct evidence, we refer to evidence obtained from studies that compare two interventions head-to-head, for example A and B, while with indirect evidence, we mean evidence obtained through one or more common comparators. Network meta-analysis is a statistical model. Like any model, it works well only if certain assumptions are met. One key assumption is called transitivity, which implies that the different treatment comparisons do not systematically differ in anything else except for the interventions compared. The statistical counterpart of transitivity is called consistency, with which we describe the agreement between direct and indirect evidence. The next step is to understand how a network meta-analysis model can be developed. There are different ways to build a network meta-analysis model, including the following. Meta-regression models, where we can treat intervention comparisons as different covariates added in the meta-analysis model. Hierarchical models, where comparisons are structured as different levels of hierarchy. Multivariate meta-analysis, where each intervention comparisons can be seen as a separate outcome. And network meta-analysis, electrical networks and graph theory, where interventions are shown as points, called nodes, and comparisons as connections, called edges, making use of an analogy between network meta-analysis, electrical networks, and applying graph theoretical methods. Let's now talk briefly about two different ways that we can follow to build statistical models, the frequent and the Bayesian approach. Some of the models of the NMA models can be adopted using the frequentist framework. This approach is quite common and works well when the model is relatively simple. But when we need more flexibility, we may use Bayesian framework. This is because Bayesian methods are better suited for handling complex structures and incorporating prior knowledge, such as in cases of rare events. So what's the difference? A frequentist model only uses the current study data. It assumes that the treatment effect is fixed and gives us a confidence interval, like saying we are 95% confident that the true effect of A versus B treatment lies between 0.5, let's say, and 1.5. A Bayesian model, on the other hand, starts with what we already know, and this is called prior knowledge, a prior. Then it updates that prior with the study data. The result is a probability of how likely the treatment effect is, and we have a credible interval. For example, we then say that there is a 95% chance of the true effects of A versus B treatment to lie between 0.5 and 1.5. All these methods for network meta-analysis are reliable and equivalent. Let's move to another important aspect that we need to consider, that is heterogeneity. Just like as in pairwise meta-analysis, heterogeneity reflects the underlying differences between the studies that directly compare the same pair of interventions. Similarly, fixed or random effects model can be fitted. The random effects model allows to account for between-study heterogeneity. To estimate heterogeneity, there are many options for estimators, including the Darsimonian LERD or the restricted maximum likelihood. Why heterogeneity is so important? Network meta-analysis estimates are combined estimates of direct and indirect evidence. Therefore, large heterogeneity in a direct estimate can affect many other comparisons which use this information. In network meta-analysis random effects models, there are different assumptions that we can make about heterogeneity. We can assume that the between study heterogeneity is the same across all treatment comparisons. This is the most common approach, especially when there are only a few studies for each treatment comparisons, as it allows for combining information across all the comparisons. Another option is to assume comparison-specific heterogeneity. In this case, each treatment comparison has its own unique level of heterogeneity. However, in practice, assuming different levels of heterogeneity per comparison can bring computational issues with a lot of parameters to estimate. Therefore, we almost always assume common heterogeneity, as we do not have enough power to estimate as many heterogeneity variances as the number of comparisons. To assess heterogeneity in a network meta-analysis, we can use the modified Cochrane skew statistic to test for its presence. However, note that in network meta-analysis, this captures both inconsistency and heterogeneity. The magnitude of heterogeneity, which can be denoted with tau square, can be also obtained and interpreted using empirical distributions from networks with similar context. Empirical distributions of heterogeneity can be derived by analyzing a collection of potentially similar network meta-analyses. Researchers can then compare their heterogeneity estimates to values from similar networks and explore if the amount of variation that they found can be considered typical or unusual. Finally, we may use prediction intervals. Prediction intervals are important to present alongside with confidence intervals. While a confidence interval shows where the true effect is likely to be, a prediction interval shows where the results of a new study is likely to fall, taking into account heterogeneity. Therefore, prediction intervals can help assess the presence of substantial heterogeneity. They are typically wider than confidence intervals, but when there is little or no heterogeneity, they are expected to be very similar. Let us see an example. In this network of treatments for reducing glycated hemoglobin in patients with type 2 diabetes, consider the comparison between treatments A and D. The network meta-analysis estimate shows a mean difference of minus 0.89, suggesting that treatment A is better in reducing glycated hemoglobin than treatment E. The 95% confidence interval excludes 0, indicating a statistically significant effect. However, the 95% prediction interval includes 0, suggesting that in future studies we may not observe a significant difference. This highlights potential between study heterogeneity. Moving forward, one of the main advantages of network meta-analysis is that it allows for the ranking of a network's interventions according to their relative efficacy. We can use ranking statistic to present a hierarchy of the treatments for a specific outcome. Based on the results of a network meta-analysis, we can calculate the probability of each intervention taking a specific rank. This is called ranking probability, and it means calculating the probability of, for example, treatment A being best, being the second best, and so on. The probability of ranking first among all compared interventions is called the probability of being the best. So for every treatment of a network, we can estimate the ranking probabilities of being at its possible rank. However, conclusions based only on the probability of being best can be misleading. So we need to consider the whole distribution of ranking probabilities. We can do that. We can see this distribution using the rankograms. In a rankogram, the x-axis shows the possible ranks, for example, first, second, third, and so on. These are the ranks that a treatment can take among all. The y-axis indicates the probability that a treatment will occupy a particular rank. In this simple network of 4 interventions, we have a separate rankogram for each treatment. This network compares 4 interventions for reducing mortality in patients with COPD. So we have these 4 rankograms, each representing a different intervention. And for SFC, the probability of ranking first is approximately 0.6, ranking second around 0.2, and ranking third or fourth about 0.1 each. So among all interventions, SFC has the highest probability of ranking first, salmeterol is most likely to rank second, fluticasone third, and placebo is most likely to rank last. We also have 2 more ranking metric options widely used, and these are the sucra values and the p-scores. Both of them provide a single metric that reflects how effective or safe a treatment is relative to all others of the network. Sucras are calculated from the cumulative ranking curve. This curve is constructed using the probability that a treatment ranks at or below its possible rank. This point, for example, is the probability SFC ranking first or second. So the cumulative ranking curve for a treatment shows how likely it is to get a high rank. If a treatment is often ranked first or second, its curve will stay high and near to the top of the graph. If a treatment is mostly ranked low, then the curve will stay lower. Now, the area under this curve is called the surface under the cumulative ranking curve, and this is the sucra. A large area under the curve means that the treatment is very likely to be among the best. A smaller area means that the treatment is less likely to rank highly. Sucra values range from 0% to 100%, and with values close to 100, implying that these are the best ranked interventions. So the larger the sucra, the better the treatment is considered. In this example, according to the sucra values, SFC ranked first. P-scores measure how certain we are that a treatment performs better than the others in the network. They range from 0 to 1, with higher values indicating better performance of treatments. A higher p-score, therefore, indicates a greater certainty that the treatment is better than the others in the network. Sucra values and p-scores are considered to be equivalent. When we have more than one outcome, scatter plots can help us show the rankings of 2 outcomes at the same time. This can reveal groups of treatments that perform similarly or well in general for both outcomes. In this example, we'll look at a network of treatments for acute mania, plotting sucra values for efficacy against sucra values for acceptability. Sucra values for efficacy are shown in the x-axis and for acceptability in the y-axis. So treatments that appear in the upper right corner of the plot are expected to be more effective and more acceptable compared to others. To display ranking for more than 2 outcomes, we can create the ranking plot using either the p-scores or the sucra values. This plot consists of concentric circles and different sectors. The concentric circles represent different outcomes. We have one circle for each outcome. The sectors represent the treatments. We have one sector per treatment. Each sector is colored based on the treatment's rank, and if a sector for a treatment is uncolored, this means that the treatment was not included in the network for that outcome. In this way, we can quickly see for each treatment how well it performed across all outcomes at once. In this plot, for example, we can see that this intervention had the lowest sucra values across all outcomes, making it the least promising. The previous 2 options are primarily graphical displays, providing a helpful overview of the results. However, there are cases where outcomes may be correlated. Modified p-scores allow the estimation of joint p-scores across 2 or more outcomes while accounting for the correlations between them. These correlations can be informed by expert opinion or explored through sensitivity analysis using a range of plausible values. Additionally, modified p-scores can allow for the incorporation of clinically important values. This helps us see how the rankings change when we consider what differences are actually clinically important. In this example of a network meta-analysis of antipsychotics in patients with schizophrenia, 3 outcomes were assessed: efficacy, acceptability, and weight change. While some interventions perform well in terms of efficacy, others may be better in terms of acceptability or weight. To identify treatments that perform consistently well across the 3 outcomes, we can use the modified p-scores. In this graph, we can see the p-scores for efficacy only and how these p-scores change when we are increasing clinically meaningful values. For a CIV, a clinical important value of 0, these p-scores correspond to the p-scores as these were originally defined. As CIV increases, we can see that p-scores and ranking changes, but clozapine, which is denoted with a red line, remains the best options across all these values. The probability of being the best can be misleading. Therefore, it is recommended to use SUCRA or p-scores as they account better for the uncertainty in the estimated treatment effects. Most importantly, rankings should not replace the detailed relative treatment effects. Ranking metrics offer an overall ordering of treatments, indicating which might be more effective or safe within the network. They are useful, but they do not provide the information that relative treatment effects do. Therefore, we should always accompany this with effect estimates and confidence intervals. To conduct a network meta-analysis, there are several options currently available. In Stata, one can use the MV meta routines to apply a multivariate meta-analysis model. Additionally, in Stata, there is also a suite of commands for generating network graphs and graphical displays. The NetMeta-R package allows for conducting network meta-analysis within a frequentist framework, including also many graph options. The GMTCR package facilitates network meta-analysis using a Bayesian approach. Both packages are available on the CRAN repository. Finally, there are 2 interactive web applications also available for conducting network meta-analysis. These are the Meta Insights and NMA Studio, and both tools use the NetMeta-R package to generate the NMA estimates. When conducting a network meta-analysis, it is very important to assess the NMA assumptions. The validity of results depends on the plausibility of models' assumptions. Then it is important to remember that ranking the interventions is attractive, but caution is always required. Understanding a treatment hierarchy should involve more than just looking at the rankings. We should take into account all the evidence from the analysis. And finally, remember that there are cases where network meta-analysis may not be feasible. When, for example, there are fewer studies than treatments, making it difficult to estimate treatment effects with sufficient power, or when we have disconnected networks. Thank you very much for your attention.